All right, this is going to be our last lesson for the year, and I'm sure you're excited about that. This is lesson 55, Inscribed Angles. It's section 12.3 out of our book. We're going to talk about the properties of inscribed angles and use those to solve problems. And there's also a corollary that deals with polygons that would have inscribed angles in them. Right, the first thing we need to do is talk about the definition chord. And I'm not sure if you've ever heard this definition or not. A chord is a segment whose endpoints are on a circle. A chord is a segment whose endpoints are on a circle. So when I look at this segment B to C, it's a chord because one of its endpoints is here on the circle at point B. The other endpoint is on the circle here at C. A chord is a segment whose endpoints are on a circle. A diameter is a special kind of chord. A diameter has endpoints on the circle, but it has to pass through the center. All right, here's the big definition for today, inscribed angles. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. All right, so right here, it's marked on your paper. This is the inscribed angle. Its vertex has to lie on the circle. Here is a chord. Here is a chord. So it says that the vertex is on the circle and the sides contain chords of the circle. This keeps on going, so it really is a ray, but it has a portion that's called the chord. Now, if you extend out your sides, right in here you are going to see an arc of the circle. The arc that lies in the interior of this angle and has its endpoints on the angle is called the intercepted arc. So when you extend these sides, it's very clear that this part of the circle is lying on the interior of the angle. That is called the intercepted arc. Now there's plenty of the circle that's out here. That's the exterior part of the circle. But this portion that's inside here is going to be called the intercepted arc. And it has the same endpoints as points that lie on the sides of the intercepted angle. All right, this is theorem 1211. It tells us how to figure out how much this inscribed angle would measure. It says the measure of an inscribed angle is half the measure of its intercepted arc. Now, the other day we were talking about central angles. So let me make a point. The other day we were talking about central angles. Central angles and the intercepted arc were the same. But now back here is where we're talking about the inscribed angle. If you think about extending these sides, you would see this intercepted arc along here. There's the arc. And the measure of this angle back here is going to be half of what this arc is. So for example, if this arc was measuring 120 along here, if that arc was measuring 120 from here to here, then this angle would only measure 60. Now you can reverse this process. If I knew this inscribed angle was 60, then twice that. Also the arc is twice the inscribed angle. So if this were 60, I would double it, and I would be able to tell you that the arc is 120. Okay, this says find the measure of arcs and inscribed angles. So the first one says find the measure of the blue arc or angle. They are asking me to find the measure of this blue arc. If I think about the extended sides of the angle's coming out here and here. So this is the arc, and I just got through telling you, if you want to find the arc, you have to double the angle. So our angle here was 90. So we're doubling that 90 to get this arc. So this arc would be 180. All right, here they have given us the arc. The arc inside this inscribed angle is 100. If I want to find this angle back over here at M, it is half of that. So I'm doing a half of 100 would make this angle right here 50. If I want to find the angle, I half the arc. If I want to find the arc, I double the angle. All right, in this case, I have the angle. I'm looking for the arc. If I'm looking for the arc, that's when I double the angle. So that will be 230. Okay. Now let's notice these angles. They are color-coded, and I color-coded your notes for today. Here's the green angle. Here is the blue angle. I'm extending their sides. The red angle extended. If you notice, all of these angles are intercepting this same arc that measures 60 degrees. So what are the angles going to measure? They're going to each measure half of 60. So that would mean each of them would have to measure 30 degrees. Now, because of what we just explored here, we're going to come up with a corollary to the theorem we've just been talking about. So the corollary says this: if two angles are intercepting the same arc, and both of these angles are intercepting the same arc, then these two angles have to be congruent to each other. I don't have to necessarily know the measure of the arc, but because they're intercepting the same arc, I can tell you that those angles are congruent. So C and D are congruent. So let's talk about this. It says that the measure of angle E right here is 75 degrees. Here is its arc. If I extend the sides of angle F out, I notice that it is intercepting the very same arc that E. Our previous corollary told us that those two are congruent, so that means the measure of angle F has to also be 75 since they are intercepting the exact same arc. All right, corollary 2. It says an angle inscribed in a semicircle is a right angle. If you notice this, I don't even need this part of the circle. This angle right here is contained within the semicircle. See the diameter here? So this angle is cutting a semicircle. This is cutting a semicircle, or it's inscribed inside the other semicircle. It's cutting a semicircle. Half of a semicircle is a right angle. So if you are working with an angle and you recognize that it is inscribed inside a semicircle, like this is perfectly contained within a semicircle, it's going to measure 90. If you can't realize that, you can extend your sides and you can say, hey, this is half of a circle, that's 180. So this angle has to be 90. All right, so right here we're going to go into some algebra. This angle at C is marked 2x. Y'all, this is a semicircle. It's inscribed inside a semicircle. So that angle at 2x has to be 90, or angle C is a right angle. It measures 90 degrees. So that means 2x has to equal 90, which means x has to be 45. The third theorem has to do with having an quadrilateral totally inscribed or drawn inside a circle. The vertices of this quadrilateral are points on the circle. So we would say that this quadrilateral is inscribed inside the circle. And this is what it says. It says opposite angles in this situation are supplementary. So all we can do about supplementary is say angle D plus the measure of angle F is 180. Angle E is opposite angle G. So they would equal 180. Now only opposite angles have a relationship here in this situation. So let's see how we could use this. In this situation, we know that we have a quadrilateral inscribed inside a circle, and we know opposite angles are supplementary. So that would mean that D plus F would have to be 180. Well, we know that the measure of D is Z, the measure of F is 80, so Z would have to be 100. The other pair of opposite angles would be G plus E, E plus G. We know that E is 120. We know that G is Y. So Y would have to be 60 in that case. All right, now this one would involve some algebra. Here's a quadrilateral inscribed inside a circle. Opposite angles are supplementary. So 3x plus 3x would equal 180. And then 3y plus 2y would have to equal 180. So those would be two equations that we would solve. 6x equals 180, so x would be 30. 5x is 180, and that should be y right there. Sorry, that is a typo. Let me go back and change that. It is a y there. Sorry, y would be 36. All right, let's keep moving. Here's our other definition that might be new to you. Tangent. A tangent to a circle is a line, and it has to be drawn on the same flat surface. And it intersects the circle in exactly one point. Now, it looks like it's touching in many points along there, but you have to remember that lines have no width and points have no width, but when we have to draw them with pencils, they do have a certain amount of width. So somewhere in here is point B, and that is the only point in which they actually touch. And your book will say lines that appear to be tangent are tangent. Sure, it looks like it's touching in more than one point, but it is a tangent. And the only reason it doesn't look like that is because when we draw a line, it has a certain amount of width to it. All right, there is one theorem that deals with tangent lines. It says the measure of an angle formed by a tangent and a chord is half the measure of its intercepted arc. Now this looks kind of funny to us. Here's the chord going across here, and here's the tangent. The intercepted arc actually loops around the chord. We're used to them being out here from side to side, but in this situation, when you have a tangent and a chord forming an angle, the intercepted arc is going to loop around that chord. It's still contained within the angle, but it just looks a little bit funny. So this angle here is going to be half this arc that loops around the chord. So the measure of angle C would be half the measure of arc BDC. In this case, the arc wraps around the chord, and I would write that on my paper. Okay, so we have some problems here that we want to look at before we end up the lesson. All right, here's this theorem we just talked about. Here's our tangent. Here's our chord. This arc that loops around the chord is 112 degrees. This arc is 112 degrees. I'm trying to find the measure of this angle back here at A. We know that the arc is associated with A is the measure of the, that should say angle there, y'all. A is the measure of the angle associated with a 112 degree arc. And so we're just going to take that 112 and we're going to divide it by 2, because that's how we find the angle. So if we divide 112 by 2, that should give us 56. So half of this would be 56. Now, I don't know if you noticed, but just like always, these two angles form a linear pair. So that means they are supplementary. So what I need to do is say 180 take away 56. And I think that would be 124. 180 minus 56 would make 124. So again, this is to me the harder of the two situations, because this arc is wrapped around that cord. So you have to see that cord and that arc looped around it. And this angle in here is half of this arc right there. Okay, one last problem. Now there's lots of stuff going on in this problem, everything we've talked about so far. Right here we have 108 degree central angle. Y'all remember that means that this arc out here in front is 108. This is the central angle. They are identical measures to each other. But now back here at angle D, think about it. Angle D is an inscribed angle. Angle D is inscribed. And it's hard for me to write with this, but it is inscribed. Remember, if it's inscribed, it's going to be half. So for D, we're going to be taking half of the 108. And so I think half of 108 would be 54. So D would be 54. Okay? Now, here's a tangent and a chord. That's what's forming angle B in here. This tangent, this chord is forming angle B. Angle B is associated with this arc that's looping around this chord. Angle B is half of that. In order to find the measure of angle B right here, I need to take half of that. So if I divide that in there, I think I'm going to get 78. So half of this 150 arc would give me angle B. Now, there are three angles here that are making up this straight line. I'm erasing some of this so we can see. Do you see those three angles? We know this one was 78, right? We know this one is 78. We know that D was 54. And we should be able to find out how much A is. If I add up 78 and 54, I think I'm going to get 132. If I add these two up, that's going to give me 132. And so those three angles make up a straight line. So if I subtract that, I think I'm going to get 48 for my angle here. And sorry, this should be C up here. So there is C. Now what is C? C is a chord that loops around angle A. Angle A is made by this chord, this tangent, this arc at C is going to be double A. So I have to take A and whatever it is, double it. So if I double that, I'm going to get 96. Now, one way you can test your answers is we said this we said this arc was 96. We said this arc out here was 108. All of those should add up to be 360 if we did that correctly. So this is going to add to that to be what, 264, and 264 plus that would be 360. So we have our answers correct.